Today we're going to be discussing graphing radical functions. We've been focusing on rational functions. We're going to take a minute and discuss radical functions. We actually did a little bit of these at the beginning of the year, so for many of you this isn't going to be too much of a stretch. We're going to start with example 1, considering the formula for the area of a square. So that formula, if area is a and if s is the side length, then we have a equals s squared. All right, so if we have a square over here, we've got the area, and then the side length is s. All right, so let's graph the function that represents area as a function of side length. Well, if my side length is x in this case, so this would mean area as a function of side length, it's a equals s squared. Notice that looks very similar to y equals x squared. It's just a quadratic function. When we have a side length of 1, 1 times 1 is 1. When we have a side length of 2, 2 times 2 is going to be 4. If I had a negative side length for some reason, I would go back here, but that doesn't make sense in the context of this scenario, right? So I'm just going to graph this half of the parabola, all right? Now, let's look at, on the same set of axes, we're going to graph, let me change colors here, the function that represents side length as a function of area. So instead of area equal to side length squared, I want side equal to something with area. So to do that, I would need to take the square root of the area. All right, that's how I would get the side. That's how I can undo this side squared and I get area. So if I graph this, let's look at this. If I have, now in this case, side is my y. All right, we've switched. If I have an area of 0, my side length is 0, right? If I have an area of 1, my side length is 1. Now, if I have an area of 4, my side length is going to be 2, so I'm going to be over here. So you'll notice we've just reflected that equation over this line right here. All right? So these equations are related by that reflection. Over y equals x. Now, there may be other relationships that you may see. If you see other relationships, go ahead and take a moment, pause the video, talk about those, think about those, write them down. Any other relationships you see. Now notice this area and side length, as we discussed, does have, let me graph them correctly, does have points over here, the area equals side length squared. It just doesn't make sense in the context of that scenario, right? But, so what we have now is a parabola, but that's been turned on its side, but it's just half of that parabola, right? So let's talk about graphing square root functions then. You'll notice this was a square root function right here, okay? The domain and range of the function is something we're talking about a lot, right? So our function is f of x equals the square root of 3x. So let's make a table of values. You'll notice we've chosen some x values that make the radicand, that's this number inside, a perfect square. So when I plug in 0 to my function for x, I get 0 here. If I plug in 3, I get 3 times 3, which is 9, which is a perfect square. So square root of 9 is 3. When I plug in 12, I'm going to get 36, which is a perfect square. Square root of that is 6. When I plug in 27, 27 times 3 is going to give me, I did not do this before the video, and I should have because I do not remember what that is on the spot. 27 times 3 is 81. 81 is a perfect square, right? And the square root of 81 is 9. All right. So for a square root function, the radicand cannot be what? So this number inside, this is the radicand when we're talking about that. This right here, radicand, okay? It cannot be negative, all right? Because it is underneath a square root, I cannot take the square root of that, or else I'm going to be getting imaginary numbers, and that is, we're not graphing on an imaginary plane. So the domain of the function then is going to be from 0 to, well, basically, it's just that. x has to be greater than or equal to 0. I could have written it the other way. I can also see that as 0 to infinity, if you want to write it that way. We've also seen it in set builder notation, sorry, which is x is an element of all the real numbers such that x is greater than or equal to 0. You'll notice this one kind of repeats that one. There are some other ways you can write that in set builder notation that we have not discussed that much. You can use also, there's the symbol for positive real numbers, if you'd like to look that up. So radical functions do not have a horizontal asymptote, right? They're going to grow. If you look at this function, it's going to keep growing. It's going to keep growing, keep growing, keep growing, keep growing, all right? They grow forever or infinitely or however you want to write that, okay? So if I graph this function that we've been dealing with, f of x equals the square root of 3x, I have these points here. So I have 0, 0. I have 3, 3. That's an odd point on this graph. There. Oh, nope, that's back here. 3, 3. It's been a little squished because we needed to get to 27. 12, 6. Right here. And 27, 9 is way up there. Alright, so we're something like this. Not perfect, but it's growing forever. Alright? So my range is never going below 0. So my range is also always greater than 0. I could also write that as 0 to infinity as well. Okay. We are, notice answering these questions, we've answered domain and range. Is the function increasing or decreasing? Well, this function, as I move from left to right, is always going up. So this function is increasing. All right, example 3, we're going to be looking at this concept that should look very familiar. We have a number when it's in front of our radical that determines a vertical stretch or compression. Vertical stretch or compression, right? H is going to determine a horizontal translation, so moving left or right. And K determines a vertical translation, so up or down. Okay. So remember that A also determines if it has been reflected. If A is negative, that will cause a reflection. All right, so let's graph a transformation of a radical function. So if we have 2 times the square root of x plus 3, notice x plus 3 is in parentheses because it's all underneath the square root. That will not always be written that way. If we look down at some examples we won't be covering in this video, x plus 4, for example, is all under the square root. It's not in parentheses. That's okay, it's still all under the square root. We do that, though, to differentiate it from the plus 2. It just makes it a little easier. You do not have to write it that way, though. So x plus 3, all under the square root, plus 5. So we need to identify what transformations map the graph of just the parent function to the graph of g. All right. How do the domain and range differ domain and range of g differ from those of f? So let's identify these parameters. So a in this case, well, a was equal to 2. So a is equal to 2. It's this number right here. So the graph has been stretched vertically by a factor of 2. So it's 2 times as tall. H is negative 3 because we have a negative under there, right? So, and we have a positive here. So H is negative 3. So the graph has been shifted left 3 units. And then 5 right here is K. So the graph is shifted or translated, if you want to use the vocabulary from up above, shifted up 5 units. All right, so if I were to graph some points, right now we have some x values here that have been chosen for us. 0, 1, notice 1 plus 3 will give me 4, which is a perfect square. If I want to do another perfect square, That means I'm going to need something plus 3 that gives me 9 is the next one. So that means I would want to do 6. So let's go ahead and do that. 6. Let's see, we have 9, then 16. That means we would want to do 13. Hopefully you see what I'm doing here. If I do 25, that means I want to plug in 22. All right, so 0 gives me 5. When I plug 0 in up here, right? 1 gives me 2 times the square root of 4, which is going to be 4, plus 5 gives me 9. 6 gives me 2 times the square root of 9, which is 3, so 6. Plus 5 gives me 11. 13 is going to give me 2 times the square root of 16, which is going to give me 8. Plus 5, plus 5 gives me 13 again. And then 22 gives me 2 times the square root of 5, 2 times the square root of 25, which is 10, plus 5 gives me 15. All right, so we have at x equals 0, we are at 5. At x equals 1, we're at 9. At x equals 6, we are at 11. At x equals 13, we are at 13. And at x equals 22, well, we don't have that on here, so I'm not going to worry about it. All right. So far, we probably should have put in some where x became equal to 0, right? Let's see. Yeah, if I plugged in -3, for example, maybe we'll just take off this 22. If I plugged in -3, for example, this would have made the interior part equal to 0, right? And I would get that 5. So -3 and 5. Something happened on our other one when we plugged in 0. Ah, that's why. When we plug in x equals 0, we do not get 5. Hopefully you guys caught that. When we plug in x equals 0, I get the square root of 3 times 2 plus 5. I get a pretty strange number, right? I'm not going to worry about that number for now. If you would like to find the decimal approximation, that's totally fine for you to do. So we have a graph that is about like that. Okay. I've just noticed that I have erased those for some reason. All right. So hopefully those transformations are making sense to you. What transformations, these are the initial questions, what transformations map that? Well, they're these transformations right here. Okay, we have these transformations that map that graph onto G. And then how do the domain and range differ? Well, the domain now, so the domain of F was from 0 to infinity, right? The domain of G, on the other hand, is now from -3 to infinity. Range of F was from 0 to infinity. Range of G is now from 5 to infinity. All right. The practice problems on your notes will be completed and posted on Canvas, so you can look at those. But that is the end of this video.